Hey everybody, how it's going? I recorded here my second video that will explain how to optimize a function using the Python language. If you want to optimize a function with a boundary conditional and with some restrictions, so be sure to watch this video and please don't forget to like, subscribe and hit that bell icon. What would function optimization be? Well, the traditional design optimization problem is defined using a single objective function. The format of this statement usually to minimize or maximize some quantity that is calculated using some design function. We can mention several examples of problems that we want to minimize, such as the dimensions of a box to obtain the lowest cost of the cardboard, the costs of a company, among others. Here, we create a fictitious function with restrictions and boundary conditions. Look, z is equal to x squared divided by y plus 6. X times y plus 4 must be greater than or equal to 0. X squared plus y squared is equal to 135. How should we do the minimization? The entire script is being shown. Look. Let's import the function minimize from scipy.optimize. At the end of this program, I will create a graph that shows the solution compared to the initial guess, and for that, I imported the function plt from matplotlib.pyplot. First, I defined the objective function, x0 squared divided by x1 plus 6. Subsequently, I need to define two constraints. The first constraint is an equality with the multiplication of all members that added to 4 must be greater than or equal to 0. The second constraint is one equation, but that will be reported at another time, not now. For now, let's define it as an equation where the sum of the all variables squared should equal 135. So, a for structure was created where the variable y goes from 0 to 1, that is range is equal to 2. In order to minimize the objective function in addition to two constraints, we must inform the initial guess and the boundary conditional. The initial guess x0 is 11.5 and 0.1, with the initial value of variable x0 and x1. The boundary conditional is defined as follows. x0 must be between 11 and 12 and x1 must be between 0 and 1. Now, let's define how constraints should be entered the minimize function. Com 1, it is an inequality, and com 2, it is an equation. Putting this information in a single block, then we'll have cons equal com1 and com2. The solution where x0 and x1 are minimized will be inside sol, which is constructed as follows. Sol equal minimize objective x0 with the method slskp with the bounds and your constraint. The solution is taken by doing xs equal sol times x. This part here is just to give the value of the answer on the screen. To create the graph, I built two x and y arrays and I used the NP point match grid function to create the ZX based on the objective function. The AX point plot underline surface command creates the 3D chart. AX point text is a command used to write the location of the gas initial and of the solution. The command AX point set underline X or Y or Z label give names to the axes. I create a second chart just to better visualize the solution. When a computer runs the program, you can see that the solution is. This is the first graph that shows the surface in 3D. To better visualize the starting point of the quake and the solution of the problem, this second graph can be observed. See that the solution is below of the initial gas and it also within the boundary conditionals. I hope you enjoyed this video and I see you in the next video. Thanks for watching. Bye!